I'm a theoretical computer scientist. What I do is I design new methods for machine learning. So most of what you guys have seen here are people using standard machine learning techniques to do new things, new applications. What I do is design new techniques that could be like state of the art for many future applications, right? And I want to talk about one such topic, something that I've researched for 10 years now, mostly on the theory side, but it's now becoming an important topic in machine learning. Okay? So I'm going to introduce a problem called the optimal transport problem. This problem has been studied since the 18th century. It is part of 3 Nobel Prizes, has a lot of applications in logistics, in operations research, and it has applications in mathematics and statistics. But only since 2000, people have started looking at this in the context of image processing and machine learning. And what I'll do is I'm going to present some very cool applications of optimal transport. Visually, they are fantastic. You'll start to wonder, oh, what all can we do with this? But there are certain challenges that come with it. It's very, very hard to compute optimal transport. It's very complicated. It's not scalable. You can take small data set and run your cool application on that small data set, it'll work fine. But if you want to scale it up, the solutions will take a long, long time to come. So it would not be practical because of lack of scalability, something that we're trying to address. And then second is that it is very, very sensitive to noise. The moment you add some noise to the data, the cool applications are no longer cool, right? They start to break down. So I'm going to talk, basically take first 10 minutes to just introduce the problem. Then the next 10 minutes, I talk about 5 different applications of optimal distance between X and Y. So a natural application of this is that it becomes a great dissimilarity measure between probability distributions. So if your 2 distributions look very similar, the amount of effort to convert one to another will be small. And if they look very dissimilar, then the amount of effort you have to put in to convert one to another will be large, right? So one can use this as a way to measure similarity between distributions. And ML, in many ML applications, for many ML applications, so there are 2 variants of the problems that are very useful. One is called the continuous optimal transport, which is what ML folks care about. And in this, your distributions are kind of spread out in a continuous space in a unit square, right? And you have 2 such distributions, and you want to understand what is the minimum cost effort to convert one distribution to the other. And but the problem is, it is impossible to compute the actual minimum cost value because it's a continuous space. There are infinitely many points. So as a computer scientist, I don't know how to compute this value, right? So what ML folks do typically is they sample from these distributions. They take some amount of samples from each of these distributions, and then, let's say n samples, they weigh each of these samples 1 over n, so it becomes a probability distribution, a discrete probability distribution, and then they measure the OT cost between those discrete probability distributions. A result from statistics says that as n, the sample size tends to infinity, continuous OT and discrete OT become the same. So for this reason, it's become very impressive and become part of things like generative adversarial networks. It has been used in the context of deep learning and so on, right? So what is the discrete OT problem? Right? So you're given 2 discrete distributions, a set of blue points in this and a set of red points. Okay? Each point, the blue points is a support of one distribution, the red point is a support of the other distribution, and at each point you have a mass associated. So if you see in the figure, there are numbers associated with each of the points. That's the mass at that point, right? And you want to transport this mass, all the blue mass to the red points. Okay? And a transport plan is simply that. It is a plan to transport mass from the blue points to the red points. The property that you want is that this transport plan has to be a coupling where the mass going out of every blue point is equal to the mass at that blue point, and the mass that is coming into every red point is equal to the mass at that red point. Okay? And the cost of the transport plan, sorry. the cost associated with the transport plan is computed simply as follows. If you're, for instance, transporting, let's say you're transporting 0.1 mass from the edge from B to A, then you simply assume the cost is 0.1 times the straight line distance between B and A. That would be the cost of that edge. And once you transport everything, so if you look at all these gray edges, they are transporting mass. Take the individual cost of these edges, add them up, that's the cost of the transport plan. And our goal is to identify the cheapest transport plan between the from the blue points to the red points. Okay? So that's the optimal transport problem. Then a special version of that is called the Euclidean bipartite matching problem, which is when the masses are 1 over n. Remember when I said that you sample from the continuous distribution and assign a mass of 1 over n for each point? If you do that, then what happens is every point has the same mass. So now if you want to transport, you can just pick a red point and a blue point, match them, and transport all the mass from the blue point to the red point. If you do that, what you end up getting is a one-to-one correspondence, what we call as matching. Okay? So this is a special version of the optimal transport problem where the optimal solution looks very nice. It becomes a matching, a one-to-one correspondence between the red and blue points. Okay, so why care about all of this, right? These problems, why are they interesting or important? You can start visualizing images, which is a large set of data, a type of data, as distributions. It's very common to do that. You can, if you want to visualize an image, let's say a grayscale image as a distribution, what you can do is you can take every pixel of the image, put a point at the center of that pixel, and whatever grayscale, normalized grayscale value it has, use that as the mass at that point, right? And what you end up getting is a distribution. So you can start visualizing any image as a distribution, okay? And this figure shows an MNIST image 7, handwritten digit 7, and how it can be seen as a probability distribution. And what you see on the right side of your, the two columns that you see, what we did is simply this. We modeled 8 as a distribution, we modeled 7 as a distribution, and then we computed the optimal transport plan between them. How does 8 get converted to 7? And what you see is the output below. You see 8 is getting transformed into 7 in the minimum cost possible way. And that's basically the idea of interpolation, which I'll talk about in a bit. Okay, so one of the first applications was shown in 2000 by Rubner, Tomasi, and Guibas, where they published, the original paper appeared in 1998 in International Conference on Computer Vision, but the journal version appeared in 2000, where they showed that OT, if you use optimal transport as a metric, you can get better results in image retrieval. So what is the problem here, right? The problem is the following. You have a huge database of images, and you get a new image. You want to know if this new image, which are the most similar images to this new image in the database, okay? Which ones are most likely the most similar images to this query image? So one way to do that is model this query image as a distribution, model all the images in your database as a distribution, and now use OT, optimal transport, to determine the cost, how similar these images are. You can take the best 7, let's say, images with the smallest OT cost to the query distribution or query image and report them. So if you see this, the image on the right, the first image in this is the query, and the next 7 images are the ones that were reported as the closest match with respect to optimal transport. And you see the query image was that of a red car, and all the next 7 images, most of them are red cars. So OT gives you a good way of sort of identifying similar images. In contrast, if you use the L1 metric, which is what typically all of us tend to use, which is pixel-wise difference, then you get pretty much garbage as a result. So if you look at the bottom, so like I said, if you use L1 distance, which is simply take pixel-wise difference to determine how similar images are, then you do not get great results in this case, right? So this was the first application in 2000. Since then, people have applied it for documents, for all sorts of stock markets, for instance, to determine how similar things are, et cetera, right? And incredible success in terms of actually detecting similar objects, right? So the second application is image interpolation. Imagine you have a dynamical system. Imagine you have a dynamical system, and what you don't know is what's happening within the dynamical system, but you have snapshots from it at time t equal to 0 and time t equal to 1. So you have some pictures of that dynamic system. You know that at time t equal to 0, this is how the system looked. You know this is how the system looked at time t equal to 1, and what happened in the middle. One way to sort of deal with that problem is take the system at time t equal to 0, model it as a distribution, take the system at time t equal to 1, model that as a distribution, compute the OT cost between them, and then OT plan, optimal transport plan between them, and then basically move the masses along this plan in a fixed velocity fashion. And what happens is you'll see the mass slowly moving from the first configuration to the second one. And that's a perfectly good explanation for what could have happened between the two snapshots. So in other words, you can take two snapshots, two images, and make it into a movie of sorts, right? So that's, let me continue and just focus on the application. Since we are running out of time, I'd rather just focus on some of the interesting applications, and I'll conclude with that. So this is the example of interpolation I was talking about. Like if you're given different objects, how do you make an object that sort of combines them in a nice way? And you start to see that you can, you use Wasserstein or optimal transport in a nice way to actually combine these objects where there are meaning to each aspect of the object. Like they're borrowing features, geometric features of the object. So in this second example, you see 4 different images on the extremes that are actually true images, and everything that's intermediate is a mix of these 4 images. Then a third application is what's called the prototype generation. Imagine, and I'm going to just use this example to explain what it is. Imagine you have at the top, there are 30 different images where each image is basically two nested ellipses. They all look different. None of them are similar to each other, right? But there is a meaning to it. They're ellipses. As humans, we can see and immediately tell, okay, these are 2 ellipses that are nested, right? The question is, can we use an automatic way of generating the fact that they are 2 ellipses, right? And so one way is to sort of use what is called median or one mean of this set of images. We could either model each of these images as a high-dimensional vector and take Euclidean distances between them and take the one mean. What you get is a garbled mess like the one that's shown here, this one, right? On the other hand, if you use optimal transport distance and you try to find a distribution that minimizes the OT distance between all the 30 images, what you see is a very interesting thing. It's an image of 2 ellipses. So it's different from all the 30 images, but it's a true representative of all the 30 images. And that's the power of optimal transport. It sort of captures the shape of the object. And this can be used in various summarization problems. If you have a large data set, you want to cluster, you want to know what these clusters look like, what's a representative, you can use it for that. The third application is color transfer. Okay, look at the leftmost column. At the top is an image, daytime image. Bottom is an evening sunset image. The question is, can I convert the first image to look more like the sun is setting? It's from sunset. Can I transfer the color histogram from the first image from the second image to the first image and make it look like as if the sun is setting? And optimal transport can be used to do this. And what you see here is outputs, various outputs. If you look at the 4 images on the right, they're not true images. They're generated images, but it looks like the sun is setting. It's just first image, but in the context of sun setting. So you can transfer these kinds of, do color transfer or kind of experiments as well. Then fifth application is in the context of generating images that look real but are fake. This is a pretty common application, right? These days you've heard of deep fake images and so on. The GAN that uses this, one of the most popular one is called the Wasserstein GAN. And optimal transport and Wasserstein distance are one and the same. Okay, so the idea is simply that you do the following. You take your generated model, the generator model, generate samples from it, take real world data, a sample from real-world data and do a matching between them and try to improve your model based on this matching. That's what really Wasserstein-Gand does. It's one of the highest cited papers from 2017. It got, I think, about 10,000 citations in just a couple of years. It's extremely heavily used. So these are the modern applications of optimal transport algorithms. I'll conclude by saying there are just two major issues when it comes to optimal transport algorithms. They're really, really slow. They're, in computational complexity terms, they're n cube. So if you have an image of 10K pixels, just 10K pixels, computing optimal transport cost between them could take up to 20 seconds. So just for one pair of images. So the biggest question, the most challenging question that people are trying to ask is, all these cool applications are fine, but can we scale this up? Can we really develop fast algorithms for these kinds of optimal transport computations? And can we build it on the GPU, for instance? Can we have a GPU-based implementation? We all know GPUs are very highly parallelizable. They actually produce solutions very fast. So can we design algorithms that compute optimal transport on the GPU? So I won't get into the technical details. We have made progress on this. We have 2 papers that are being presented as of now, starting tomorrow in a conference called NeurIPS, which is the best conference for machine learning. These are results where we have given a GPU implementation that actually outperforms the state of the art. The other issue, and this I'll conclude with this, is the following, that OT is very sensitive to outliers. So if you look at the images on the left, 8 and 8, they're 2 different 8s. If you compute the OT cost between them, it's 0.044. In the second one, there are 2 different digits, 8 and 7. If you compute the OT cost between them, it's 0.066. In the third one, what I've done is I've added background noise in the second image. They're both 8s. We can tell they're 8. But in the second image, there's background noise, some white noise in the background. The cost goes up to 0.081. So the cost becomes higher in the presence of noise, more than when you look at dissimilar images like 8 and 7. It's more than that. So then the moment noise comes in, even similar images become dissimilar with respect to optimal transport. So how do you overcome that? And we came up with a very interesting way of sort of automatically extracting noise out of the system. This was presented in ICLR, which is another top-tier machine learning conference this year. I won't get into the details simply because we are out of time and I want to respect potential future speakers, so I'll just stop here. Basically, my takeaway message for you guys is, if you're doing any ML application, apart from all the standard techniques that you know of, also consider using OT. You may get really nice results. This is a very new tool, immense applications, shows up in all sorts of deep learning, the loss function in deep learning, for instance, etc. So it can be used in many nice ways to get high quality results. So with that, I'm going to stop. Thank you.
Computing such kind of high-ended image processing, do you require really a supercomputer or anything, or what kind of platform you'll be using for your research?
So that's a very good question. Right now, that is the answer, supercomputers. As engineers, when we can't do anything well, what we do is we put more resources in, hoping that we can do things well, right? I am doing the opposite. I'm trying to make these things faster. And that's where I think the research focus is. Can we understand these methods, make them faster, so that we don't need these other high-end resources? So the research I would suggest people to do is to actually look at these optimization questions, see how you can scale them up, how you can make them one scan. Look at the data once and it produces the answer, right? Those kinds of things are like,
simulation would be helpful? Simulation model will be helpful?
Yeah. I mean, optimization-wise, algorithm-wise, what can we do to make it really scalable, right? That's the question that I have. But right now, what people do is really that. That is why Facebook and Google produce the best result, because they have so many resources. They'll throw it onto the
So that's the challenge
the
for
application.
research, future research.
Yes, that is why I consider future research to be how do you eliminate the need for these high computing resources, high performance computing resources, right?
Thank you so much, Dr. Sharath, for a wonderful presentation.